Another fluid property that's also used a lot is actually what we call the specific gravity. Sometimes we call that actually the relative density. So I'm giving you the common and less used names of that properties here. So relative density or specific gravity, it's clear. It takes the symbol S subscript G capital. S coming from the specific and G is coming from gravity. But it's also known as relative density, which it's give you the impression that it's rho over rho. But when you do relative use, usually you reference your property to a very valuable one. So the very and the most valuable fluid in our life is actually water. So if you divide the density of any liquid or gas, I would say in general, of any fluid, right? Divided by the density of water, this is what gives you the specific gravity. So for example, what is the specific gravity of water? It's going to be the density of water reference to the density of water. So the specific gravity of water will be 1. If you want to do the specific gravity of mercury, it's going to be the density of mercury divided by the density of water. And we know that density of mercury is 13,600 divided by 1,000. That's going to be 13.6. If you want to do the specific gravity of air, it's going to be the density of air divided by the density of water at the ambient condition. This is 1.2 divided by 1,000. And as you can tell, it's density over density, so it's actually a dimensionless number. You can write that kilogram per meter cube of fluid A divided by kilogram per meter cube of water is going to be the same. In most of the books actually, they use here 998, which is actually the density at approximately 4 degrees C and P atmosphere. But again, for simplicity, we are using actually 1,000 as a rounded number. So that's why I'm using 1,000 in the denominator here. So again, this is raw water 1,000 divided by raw water, which is 1,000. That's why the specific gravity is coming to be 1. So that's the definition of specific gravity. It's simply a ratio of the fluid density divided or reference to the density of water. And that's conclude the third fluid properties of interest. And let's move to the next one. So the next property actually will be what we call the specific volume. And we usually give that the symbol of V small, okay? So V stands for the specific volume. Remember, volume, we give it V capital or V capital with a line in the middle. So specific volume actually is simply the volume of unit mass. So if you bring a container and in that container you dump 1 kilogram of liquid or fluid, say water, so that's now the unit mass in here, then you measure the volume of that unit mass. This is what we call the specific volume. So specific volume by definition is actually the volume of unit mass. So it's symbolically as the volume divided by m. So the unit of the specific volume is actually meter cube divided by kilogram. Does that remind you of any specific property that we covered in the previous videos? Yeah, if I flip this, what I'm getting, we know that rho, which is the mass density, is simply the mass over the volume, which means that V and rho are actually the flip of each other. So specific volume is volume over mass, or simply it's 1 over the density. So that's the relationship between velocity, specific volume and the relative density. For example, if you want to get V of water, is going to be 1 over the 1000, which is the density of water, so it's going to be 0.001, and this is meter cube per kilogram. If you want to get the specific volume of mercury, it's going to be 1 over 13,600, whatever that number is. Again, it's meter cube per kilogram. And do the same for the air. Specific volume for the air is going to be 1 over 1.2, whatever that number is. You can get the specific volume of the air. So these are the very basic fundamentals so far. One more property that we're going to talk about in the next video is going to be actually the viscosity, which is very crucial to understand for the coming few videos as well. So let's talk about viscosity in the next recording.